Welcome, everybody. Thank you for joining. My name is Stefano, and I work as part of the Confidential Computing Consortium, bringing you a list of different project webinars in 2021. This one's going to be circling around Occlum, one of the projects that's part of the CCC. And we've got Tate and Zongmin here from Ant Group to go over the project for you. So I'll go ahead and pass off to Tate.
Hi, everyone. This is Hongliang and Zongmin. We are from the confidential computing team at the Ant Group, and we are glad to be here to give an introduction about the Occlum project. And so here is the content. So first, the first part is a very brief introduction to the Occlum project. We'll talk about the architecture and how a typical user would use Occlum to run your application inside SGX enclaves. And the second part is about the new Intel SGX on the then scalable processor Ice Lake, and we'll give a benchmark of the performance of the new Intel SGX and see which part of SGX speed up, which slow down. The third part is the main part of this talk. It's about how we have started this new product called the next gen Occlum, and in which we have optimized the LibreOS for this new generation of Intel SGX and achieve some very good performance numbers. So let's start. So what is Occlum? The goal of this project is to empower everyone to run every app inside enclaves. So this very simple goal, and this is the architecture of this project. Occlum is LibreOS. It's the LibreOS for SGX enclaves. So inside the enclave, we got a LibreOS, which consists of a number of subsystems like virtual memory, process management, inter-process communication, file system, networking, etc. And so with this LibreOS, you can have unmodified program applications. They can just call the LibreOS syscalls, which is compatible with Linux syscalls. So unmodified Linux binaries can run inside enclave, and you can have multiple of them. So we have a multi-process support. And the LibreOS will interact with the host OS for the trusted apps in a very safe and secure way. For I/O, we do transparent encryption and decryption for disk I/O. So this is how it works in a very high level overview. And from a user's perspective, you got an Occlum command line tool to use the Occlum. The most important two commands are build and run. So in a trusted development environment, you use the Occlum build command to convert your rootfs. So this rootf is everything you need at runtime to run your application. For example, the binaries, the libraries, any configuration or data files. This is the rootfs. So you should provide this rootfs, and the build command will convert this rootfs into an Occlum trusted image. This new format is MAC protected and optionally can be encrypted. So this trusted image will be uploaded and to the untrusted deployment environment. So at the untrusted deployment environment, you use the Occlum run command to start a new enclave, and the LibreOS will load the image. So So the LibreOS will check the integrity of the Occlum trusted image, and every I/O to the storage will be encrypted. So this is how it works. Okay, the next slide. So here is to give you a feel about how Occlum works in practice. This is a Hello World demo. So we got a Hello World program, and then use GCC as you normally do to compile the program. Now you have a Hello World program that can run on Linux. So our goal is to run this unmodified Linux program inside SGX enclave with Occlum. The first command is Occlum init. It's kind of like the git init command that we by using this command you turn the current working directory into an Occlum context. So we have some for example, after the init command, you got an image directory. So this image directory is the root.fs that you should provide. So you copy the Hello World program into the image directory. Then we can use the build command to turn the image directory into an Occlum trusted image. And now we can use the run command to load the image and start the enclave, and LibreOS will run your program. This is how simple it is to use Occlum to run an unmodified Linux program inside SGX enclave. Oh, sorry. Okay, we're back. You can find more demos on the Occlum's GitHub repository. We have multiple demos for different programming languages, and also demos for popular applications, as shown here. The next part is the new Intel SGX, which is just launched by Intel very recently. So this new generation of Intel SGX is available on the 3rd gen Xeon scalable processors, Ice Lake. What's new about this new Intel SGX is first of all, it has a relaxed threat model. So its target use cases are where the physical environments are trusted. So it relaxed some protection against the physical attacks, but it still holds all the promises about protection against cyber attacks. And so the threat model is relaxed, but what you got in return is improved scalability. You have first of all, you have very huge enclave memory. Actually, the enclave memory is up to 1 terabyte. So this is very large improvement over previous generations of Intel SGX. And the second is that you can have many cores. So on the scalable processors, you got at most I think it's 80 cores, 80 physical cores. So this is a huge step compared to previous generations, and you can have a two socket Xeon scalable processors with up to 80 physical cores. So the performance of the next gen, the new Intel SGX, is expected to be great. So we have conducted some performance evaluation. We specifically we are interested in the 3 types of SGX specific overheads, which are enclave memory access, enclave dynamic memory management (EDMM), and enclave switching. We compare the 3 different SGX implementations on 3 platforms: Pentium Silver, which is a low-end Intel processor, and Xeon E3, which is the previous generation of Intel's SGX offering on for data center servers. And the third one is, of course, the Xeon SP Ice Lake. So you can see the differences between these three generations of SGX platforms. Their EPC size, whether they support EDMM. Okay, so here is the so what we want to know is whether these SGX hardware overheads disappear or they stick around. And so here is the results of the enclave memory overhead. As you can see, as the working memory of an enclave increases, the normalized access latency of enclave memory access latency of enclave memory it stayed the same for Xeon Ice Lake, but for Pentium Silver and Xeon E3, they have grown tremendously when the working memory of an enclave exceeds the EPC size. So so the memory access latency inside enclaves on Ice Lake has indeed tremendously greatly reduced. The second aspect is the EDMM. So we have measured the cost of allocating enclave pages or deallocating enclave pages dynamically on Pentium Silver and Xeon Ice Lake. As you can see the results, the blue line and the red, the yellow line are about at the same level. So so the EDMM costs on Ice Lake are still there. Yeah. The third aspect is the enclave switching, and there are two standard methods that you can trigger enclave switching, which is the CPU enter into the enclave and it exits enclave. This is enclave switching. So the standard way to do this is to echo and occl. Echo is a structured code inside the enclave, and occl is calling untrusted functions from the enclave to the outside. So this so we have measured the cost of eCall and occl respectively on 3 different platforms. As you can see, they are quite expensive. To put the numbers into perspective, the cost of system call is around 100 CPU cycles. So enclave switching overhead is much greater than a normal system call. So this is very expensive. But what do we see on Xeon Ice Lake is the enclave switching did get some performance improvement, but the cost is still high. Yeah. So as this benchmark shows, that Xeon Ice Lake on the new Intel SGX indeed has some very good performance improvement, especially in the memory access latency, but the EDMM cost and the enclave switching cost is still there. So as software developers, as the designers of a library OS for SGX, we need to take this into consideration and think some ways to improve the performance. So this is why we start the next gen Occlum project, which is an experimental fork of the Occlum project, that we want to take some radical changes to the Occlum project for the optimal performance for new SGX. As you can see, the consequences of the high cost of enclave switching is that the performance, the I/O performance of library OS will be affected, and the high cost of EDMM will impact the memory management performance of the library OS. So this is the consequences of the hardware SGX overhead, and we this is a problem. And we also make some observations. The first is that on this new Intel SGX, we get many more CPU cores. So with this increased number of CPU cores, we can try to do more to increase the parallelism, so that we can have a higher CPU utility. And since we got many more cores, we can try polling-based I/O instead of interrupt-based I/O. And the second observation is that since we have more unclip memory, we can try to make better use of the memory and do more caching and pooling to improve performance. So based on these observations, we have introduced a new design for the next gen Occlum, which we call it asynchronous-centric design. So this asynchronous-centric design manifests itself as 4 levels, from bottom to the top. They're the language level, which is we need to answer how we can express async logic easily, and at the scheduling level, we need to find a way to execute async code efficiently, and on the I/O level, we need to figure out how to perform async I/O efficiently, and finally at the kernel level, we need to fulfill our ultimate goal of accelerating the system calls. So there are some new async techniques that we have used to accelerate the LibreOS. So I will dive into each one of the 4 levels. The end result is we can deliver a close native performance on some of the most OS intensive workloads with this async-centric design. So what is asynchrony? According to Wikipedia, asynchrony, the ultimate benefit of asynchrony is that it is to increase parallelism. So this is the increased parallelism that delivers better performance. Okay, so to do asynchrony, we need to express the async logic, the async code, and we need to write very complex async logic easily. So this is why we need to find a better programming language support for async programming. And as you can see that there are some for a language like a JavaScript, which is very heavy with async programming. It evolves from callback-based async programming to promise-based async. Promise is an object that represents some async I/O, async tasks that will be completed in the future. So this is promise-based async programming, and finally it evolves into this async await paradigm that allows a programmer to express async logic in a synchronous way. As you can see, this you just write a async version of the function, and you express it as if this is just normal sync code. So async await is a good programming feature that can allow developers to write async code easily. And as you may know that Occlum is written in Rust, and fortunately, Rust is the first system programming language that supports async await. So with Rust async await support, in next gen Occlum, we can express the async logic very easily. So and the async await feature in Rust follows the zero cost abstraction. Is that there are just minimal overhead with this new async await feature, unlike JavaScript or Go, other program language. Rust single wait feature is very efficient. So this program language foundation for us to make this asynchrony transition. And the second level is that so now we can express async code, but how can we execute this async code efficiently? So this is why we introduce a coroutine based in-enclave scheduling. As you can see, so at the library space, we have so the scheduling, the units for scheduling are coroutines. And coroutines are very lightweight. They are very fast to create and destroy and have a minimal memory footprint. And we do the coroutine scheduling completely inside the enclave. So the context switching between coroutines, the scheduling is very efficient, and we map the unlibrarized coroutines onto P host threads. And for this coroutine, some of these coroutines run librarized tasks. Some of these coroutines run user tasks. So user threads are just a kind of a special type of coroutines. And although we use coroutines for scheduling, we can still do a preemptive scheduling. So we'll handle interrupt, periodic interrupt, so that user threads can be forced to do context switching. Yeah, and the librarized coroutines are scheduled cooperatively. So librarized tasks are very efficient, are very can be scheduled very efficiently, and the user threads can be scheduled. Yeah. Okay. So with this coroutine-based in-enclave scheduling, we get increased librarized parallelism with very minimal overhead. This increased parallelism is no doubt very good for performance. And the third level is the IO level, and we want to do IO more efficiently, especially that we don't want to do any enclave switching. So this is why we have introduced an IO ring based switchless async IO. So with this, in this new mechanism, we utilize the IO ring interface that is first introduced in Linux kernel 5.1. And the idea of the IO ring is that a Linux application like Occlum can submit request to the Linux kernel by just pushing, just do some pushing requests into a shared ring buffer, and the Linux kernel will use a kernel thread to pull this pull request. So there are no enclave switching, and to get a response, and you can it's also use a shared ring buffer for completion. And so the library does not need to exit the enclave to gather responses. The Linux kernel will push the response into the ring buffer in the shared memory, and the library can just pull the response out of it. So there are absolutely no enclave switching, and also no user kernel switching. So this is very efficient. So and most importantly, IO ring provides the true async IO interface. Before IO ring, there are no efficient and async IO interface on Linux. So with IO ring, Occlum can do true async IO async IO in a switchless and very efficient way. the most important is at the language levels of scheduling and IO, we got some good foundations that for us to improve the performance of LibreOS, but we still need to introduce new async techniques to really accelerate the system call implementations. So we have introduced two new classes of async techniques. The first one is called eager execution. With this technique, we perform some very time-consuming operations in advance, so that when the system call to the LibreOS arrive, the result is already there, and it can be returned immediately. This is most effectively for read-like system calls. Let me give you a concrete example. So here is that accept Cisco. Accept Cisco is for a listening socket to accept new incoming connections. So so in a traditional the traditional way to implement this accept system call in LibreOS is showing this diagram. The trusted app inside the enclave will do a LibreOS system call to submit the accept Cisco. This is for the LibreOS. The LibreOS, after accepting this system call and do some pre-processing, it eventually has to delegate this system call to Linux, because the LibreOS is at the user space. It cannot do real I/O, so it has to turn to the sorry. Okay. Oh, it's back. So the LibreOS has to eventually turn to Linux to process the accept Cisco. So an enclave switching has to be triggered here, and which is very costly. So this is how traditionally this accept system call works. If you use some switch list technique, you can eliminate the enclave switching part. So the overall latency of the accept LibreOS call is reduced. But you still have to wait for Linux to complete the accept system call. With our async approach, we can greatly reduce latency. In most cases we don't even need to wait for Linux to complete the accept Cisco. The trick is here that so as long as we have a listening socket, we'll send several async accept requests to Linux in the background, and this is all async ring request. So it's very likely that even before the user call the accept Cisco to the LibreOS, we'll have some of the accept request complete. So and the LibreOS will maintain a backlog of accepted connections. So when the LibreOS receive accept Cisco from the trusted app, we can just return the accepted incoming connections to the user. So there is no so the latency, the perceived latency of the trusted app does not include the accept system call to the Linux kernel. So the performance is greatly improved. And for the rich system call, we can do a very similar trick. And with the async approach, we can do async even before the user request. We maintain a page cache for files so that we can prefetch prefetch data for sequential file writes. And for sockets, we maintain receive buffers so that even before the user, the trust app request some socket data, we can submit a async receiver request to Linux and store the data inside the library-wise receive buffers. Okay, so this is eager execution. Another class of async technique is promised execution. The idea of promised execution is to delay the execution of some time-consuming operations, so that we can immediately return the system call. And the challenge here is that if the library has returned the system call immediately, it has to keep the original asynchrony semantics of the system call. For example, we can use this promise execution technique to accelerate the write-like system calls. So here is an example. Just like the accept and the read system calls, and in the traditional approach, you have to trigger enclave switching. And with a switchless approach, and the enclave switching overhead can be eliminated, but the latency of the write system call still includes the latency to Linux. So in our async approach, we can eliminate the Linux latency from the library latency. The idea is here. After the libraries receive the write system calls, we will write the user's data into page cache for files, and for socket we'll store the data inside the send buffers. So this ways we can immediately return the write system calls, and sometime later we'll submit the dirty pages inside our library's page cache to Linux, or we can flash the send buffers of the send buffers that the library maintains. Flash these send buffers to Linux kernel. So with this async technique, we can eliminate the real cost of Linux write system calls from the liberalized write system call. Okay, we can do similar trick with memory map system call. And okay, so with this AsyncCentric design at these 4 levels, we can achieve a very close to native performance with this IO intensive system calls. So here is the implementation status. The next gen Occlum branch is being developed in parallel to the master branch of Occlum, and we have made a tremendous amount of changes to the library OS, and the next gen Occlum will replace the master branch of the Occlum after Intel. This is the next gen Occlum branch will replace the master branch of Occlum recently. Okay, so here is the experimental evaluation. What the question here is, we want to measure how close is the SGX application can perform to its Linux counterpart. So we would ideally, what we want to achieve is ideal with content computing is that we want to have a minimal performance, which we call it the confidential computing with confidence in performance. So in this regard, we have to do this external evaluation with Linux as a baseline. We don't want to compare with the previous versions of Occlum. This is not users really care. What user care is about how SGX performs compared to Linux. So the baseline is Linux, and the hardware platform is the Xeon scalable processor S Lake. And we have three micro benchmarks, which are scheduling, networking, and file I/O. So here's the result. So for this scheduled system call latency on Linux and NGO, as you can see, they are on the same bar. So the scheduling performance of next gen Occlum is on par with that of Linux. And for socket I/O, and we write an event loop-based I/O ICO server. And use this as our benchmark. So you can see as the number of concurrent connections increase, and the overall I/O throughput of this server on Linux and NGO is on the same level. So the network I/O performance of NGO is quite close to that of Linux. And this is file I/O, and since the page cache has a great effect on the I/O performance, file I/O performance, so we need to separate the two cases. When the page cache are all hit, or page cache or miss. For when the page cache or all hit, Linux performance and NGO are very close, since the file I/O is basically just memorized. And so this is the result. And when the page cache hits is 0 or close to 0, and so this is when I/O really happens. This is when you have to really to reach to the disk to complete the I/O request. So as you can see, the blue line of NGO and the yellow line of Linux are quite close, even in this case. And for RISE, the performance of NGO is even greater than that of Linux. This is due to the fact that NGO is accelerated with I/O ring. I/O ring is the fastest I/O mechanism on Linux. So NGO has benefits from the use of I/O ring. Okay, so for unencrypted file I/O, the performance of NGO is on par with that of Linux. And to wrap things up, here are the key takeaways. The new Intel SGX on Xeon Ice Lake offers increased scalability in terms of CPU cycle, CPU cores, and enclave memory. In the next gen Occlum project, we have re-architected Occlum with the new AsyncCentric design. And this new design is empowered by Rust async await feature, and we found that this is really great. It allows you to write economic code with very minimal runtime overheads. And one benefit of your using I/O ring behind the scene is that we can enable legacy apps to leverage Linux I/O ring, because usually you for a Linux application to use our I/O ring, you have to make changes to your application to use that. and the change could be structural changes to your program. But by using our Occlum library OS, your application can benefit from Linux library transparently, which is we think is very great. And the next gen Occlum will be merged into Occlum in a very near future. So so that's all. And Zomi and I will be ready to take any questions. Thank you.
All right, I don't see any questions in the queue. I'll give folks a minute in case they're mid-typing.
Mm-hmm.
Okay.
Okay.
Well, thanks everybody for joining today, and thank you very much, Tate, for the presentation, and appreciate everybody joining. Thanks all.